So I'll be going over how to find the integral of radical x squared plus 1 over x squared dx. And in order to solve this integral, we're going to make use of trigonometric substitutions. And I'll walk you through the basic steps in case you haven't ever come across a problem where you had to use trig subs. But basically what we're going to do is we're going to make use of right triangles and their properties, and we'll begin by letting x equal tan theta. And when we do that, we'll find that the derivative of x dx is equal to secant squared theta d theta. Our next step is to look at all of our x values in our original function and to replace them with the tan theta that we've assigned the x value. And when we do that, we're left with the square root of tangent squared theta plus 1 over tangent squared theta times secant squared theta d theta is equal to our original integral. And we can go ahead and simplify the numerator by making use of the fact that there is an identity that says that tan squared theta plus 1 is equal to secant squared theta. So just like that, we're going to go ahead and modify the function so that we have the square root of secant squared theta over tangent squared theta times secant squared theta d theta. And what we'll do next is we'll go ahead and we'll make use of the fact again that the identity says that secant squared theta is equal to tangent squared theta plus 1, and we're going to assign that to the secant squared theta that's outside of this fraction. And it'll become clear while we do that in the next few steps, but effectively what ends up happening is we're left with, we'll cancel out the square root, making use of the fact that this is secant squared theta, and we'll have the integral of secant theta over tangent squared theta times 1 plus tangent squared theta d theta. We'll distribute this fraction into both of these terms, and what we're left with is secant theta over tangent squared theta plus secant theta times tangent squared theta over tangent squared theta d theta is equal to our integral. And we'll simplify this further by canceling out these tan squared theta, and what we're left with is the integral of secant theta over tangent theta d theta plus the integral of secant theta d theta. Now, this integral of secant theta d theta can have its own video in which I'm solving it, but for the sake of time, I'm going to just go ahead and assume that you already know that integral, or you know how to use Wolfram alpha. And we're going to make use of the identities of secant theta and tangent theta to further simplify this integral over here. So you'll see that I've converted secant theta into 1 over cosine theta, and I've converted the tangent theta into, this should be tangent squared theta, into sine squared theta over cosine squared theta d theta. Now we're going to go ahead and cancel out the cosine in both of the denominators in this complex fraction, and we're going to add this entire integral to the integral of secant theta d theta, which happens to be ln of the absolute value of secant theta plus tangent theta, and we can't forget our constant. So this function needs a little bit more modifying before we can really do anything with it, and what I ended up doing here was converting this cosine into cosecant theta times cotangent theta d theta, making use of the fact that sine squared theta is in the denominator, and that cosine theta would allow us to modify this function. So the integral of cosecant theta times cotangent theta d theta I've already done for the sake of time, and that is equal to negative cosecant theta. And we're going to go ahead and add on our original, we're going to go ahead and add on this part of the integral that we solved for when we solved the integral of secant squared theta d theta, which is just equal to ln the absolute value of secant theta plus tangent theta, and of course we can't forget our constant c. Now here's where the trig part of the trig substitutions comes into play. Now, we'll make use of the fact that when we originally set our x equal to tan theta, there were some implications regarding the values of x. For instance, if we were to take if we were to make use of the fact that x is equal to tan theta, then we could draw a right triangle in which we had a theta, and the values of tangent theta would have to be equal to x, or x over 1. So the definition of tangent is opposite over adjacent to the angle, and our x would be the opposite, and our adjacent value would be equal to 1. And we'll make use of the fact when we use the Pythagorean theorem that our hypotenuse will equal to the square root of x squared plus 1. Now, given this solved triangle, we can also find the values for cosecant theta and for secant theta, and I've written them out here for simplicity and to save some time. But if you really want to go ahead and go back and check to make sure that everything is follows from the original definition of our x values, then you're more than welcome to. What we will eventually be left with is, once we plug in our tangent theta, cosecant theta, and secant theta wherever we see them in the solution, what we're left with is negative square root of x squared plus 1 over x plus the ln of the absolute value of x squared plus 1, which we took from the secant theta, plus our tangent theta, which is just equal to x. And then, of course, we can't forget our constant plus c.